Hi, my name is Leen, and in this video I would like to talk about updating firmware or MCU boot on the RA series of microcontrollers. Now, all microcontrollers require some form of memory to be able to function efficiently. Typically they use RAM or random access memory to store volatile data such as variables, ROM or read-only memory to store firmware, and this is nowadays nearly always flash that can be programmed in circuit. And often they also need some form of non-volatile memory to store small amounts of data, for instance for calibration data. Traditionally this was an external EEPROM or electrically erasable programmable memory IC that was accessible through I2C or SPI. In the case of the RA, this is replaced by an internal version called data flash. Here we see the memory map of a typical RA device, the RA6M3, taken from the user manual. This microcontroller supports a 4 GB linear address space that can contain both program and data. The memory map is built up with several designated spaces for different types of memory, as well as specific locations for registers that control the operation of the microcontroller. The flash block is dependent on the size of the flash in the particular version of the MCU. In this case, the RA6M3 can be either 1 MB or 2 MB of flash. The flash can be programmed in 128 bits units and erased in 8 KB or 32 KB units. The flash memory is divided into 37 or 69 blocks of either 8 or 32 KB, depending on the total flash size. And there are several security features available for flash, such as area protection, which enables rewriting for selected blocks only and disables programming for other blocks, and also protection against illicit tampering with or reading of data in flash memory. The RA series of microcontrollers support various methods to program in-circuit flash. Method 1 makes use of the inbuilt hard-coded bootloader that is always present in the device and makes use of one of the serial ports. Method 2 is identical to method 1 but makes use of a USB port if the RA device has one. Note that the device must be placed in boot mode with the MD pin prior to powering up to enable method 1 or 2. Method 3 makes use of the debug port, either JTAG or single wire debug, and makes use of an external debugger. And method 4 makes use of an internal routine and enables the microcontroller to reprogram itself once a firmware update has been received. That's what we're talking about in this video. So why would you want to reprogram a device once it leaves the factory? A deployed device in the field may need to have its firmware updated due to new requirements, functionality improvements, bug fixes or security features. It's not always possible or practical to reprogram the device on site or have the devices returned to the factory for upgrading. Therefore, Renesas has developed a methodology to update the firmware of RA devices in the field, and this toolkit is called MCU Boot and has been integrated into the FSP and it supports all RA devices. So what is MCU Boot? Well, MCU Boot is a secure bootloader for 32-bit MCUs. It defines a common infrastructure for the bootloader and defines system flash layout of microcontroller systems and provides a secure bootloader that enables easy software update. MCU Boot is operating system and hardware independent and relies on a hardware porting layer for the device being used. MCU Boot is an open source project hosted at MCU Tools GitHub project and is currently managed by the Leen community project. MCUboot handles the firmware integrity and authenticity check after startup, and the firmware switch part of the software update process. The operation of switching of the firmware from the original image to the new image depends on the image upgrade methods, which we'll talk about in a minute. So how does MCUboot approach the booting process? For applications using MCUboot, the MCU memory is separated into MCUboot, primary app, secondary app, and the scratch area. Here you see an example of the single image MCU memory map. The functionality of the MCUboot during booting and updating is as follows. The bootloader is started when the CPU is released from reset. If there are images in the secondary app memory marked as to be updated, the bootloader performs the following actions. 1. The bootloader verifies the integrity and authenticity of the secondary image. 2. Upon successful authentication, the bootloader will switch to the new image when in swap mode, but in override mode, this will happen if the version of the update is the same or greater, or downgrade protection has been disabled. 3. The bootloader will boot into the new image. If there is no new image in the secondary app memory region, so in normal operation, the bootloader will authenticate the primary applications and boot the primary image. So there are several different update strategies. The first one is overwrite. In the overwrite update mode, the active firmware image is always executed from the primary slot. And the secondary slot is a staging area for new images. Before the new firmware image is executed, the entire contents of the primary slot are overwritten with the contents of the secondary slot, or the new firmware image. This happens as follows. Primary slot, original firmware version, secondary slot, updated firmware version. It's copied into the first firmware version and then put it. Another one is swap mode. In the swap image upgrade mode, the active image is also stored in the primary slot and will always be started by the bootloader. If the bootloader finds a valid image in the secondary slot that is marked for upgrade, then contents of the primary slot and the secondary slot will be swapped. The new image will then start from the primary slot. This has obvious advantages in that you can revert to a former firmware version. This goes as follows. The original firmware, the updated firmware is copied to the original, to the primary location, and the original firmware is copied into the secondary location, and subsequently the device boots into the primary app, which is Rev2 in this case. Another strategy is direct execute in place, or XIP. In the direct execute in place mode, the active image slot alternates with each firmware update. If this update method is used, then two firmware update images must be generated. One of them is linked to be executed from the primary slot, memory region, and the other is linked to be executed from the secondary slot. As follows. You have revision 0.1 in the primary slot, which is active, and you have an updated version in the secondary slot. Primary version is active at this stage, but if you want to switch, you activate the second one, and then the device boots into the secondary area. Crucial to the MCU boot process is getting a new firmware version into the microcontroller. The transport interface for new updates is completely application dependent and is not included in the MCU boot stack. It can be via USB, PC, DC, and the X modem protocol, USB mass storage by inserting a USB stick, TCP IP, or whatever method you would want. It's expected that the user will have different requirements for how a new image should be transferred to the device, depending on the interfaces available and to what degree the device is physically accessible. Key to the usability of MCU Boot is security. Simply said, if MCU Boot cannot guarantee the trustworthiness of the firmware update, then MCU Boot does not accept it. Simply said. As already mentioned, MCU Boot is supported on all RA devices. You must however keep in mind that having two firmware versions in memory effectively halves the size of usable flash. Renesas provides an example project bundle for all of their RA evaluation boards. These demonstrate most, if not all, of the peripherals on a device. In addition, Renesas provides a complete design package of all of its evaluation boards, including schematics and Gerber files. Example projects are available for all peripherals and are periodically updated and expanded. This is the RA6M3 MCU block diagram. Most notable features are the large amount of flash and RAM, in addition to high-performance peripherals such as graphics, TFT controller, Ethernet, 12-bit ADCs and DACs, and powerful timers. Renesas has several dedicated MCU Boot example app notes. Simply search for these app notes designators on the Renesas website. The MCU Boot APIs are fully documented in the EFSP documentation. I will now demonstrate a modified MCU Boot example on the EK RA6M3 in swap mode with X-modem update capability. I will program the Secure Boot bootloader into the RA6M3, use a modified linker script in the application so the application is linked to the primary slot memory address, build and sign the application binary, download the signed binary to the primary slot, the first time using J-Link software, modify the application, build and sign it, and then connect to the original application using TeraTerm via the USB PC-DC interface and download the new signed binary using the X-modem protocol. That is effectively the firmware update. Here we have the test setup with the EK-RA6M3 evaluation board. The connections are as follows. Here we have the debug connector. Here we have the CDC serial connector. And here we have a serial connector connected to the Arduino headers of the serial port. What we'll now do is as follows. We'll first develop an application, a simple application to flash 3 LEDs. Subsequently we'll load the bootloader, and subsequently we'll modify the initial application to only flash 2 LEDs, so you can see that's a different application. And once we boot the device again, the bootloader will transfer the secondary slot image, if first validated, and then transfer it to the primary slot. Here we have the E-Square Studio project opened up with the Blinky program, following the instructions in the lab. We've copied the pre-configured sources into our project. The pre-configured sources, the pre-configured image creation scripts, and the signing keys. Here you see that we've added the USB PC-DC stack into the downloader thread, and in the HAL common thread we have the usual stacks. So in the Blinky thread we'll have the standard project, which is in the E-Square Studio, where the 3 LEDs of the board flash on and off. In the signing tool we can open with the text editor. we can set the version of the program that we want to that we're making, and here is version 1.01, which is correct for the first version in this case. We generate the project content, of course, and we build it. But in the debugging scenario, we have to modify the location where it's located, and that has an offset of 10,400. Now we can launch the project at this offset, because normally it's is launched at 00, by simply clicking debug. It's loaded to the target and starts running once I press F8 or run. And now if we have a look at the actual now we see that the 3 LEDs are actually flashing. The next stage is that we download the actual precompiled bootloader to the application or to the target, and we do that with this batch file. So I open up a command line to the downloaders subdirectory, and we call this file, and it's loaded into the device. If we now have a look at the output window of the serial output of the bootloader, while we press reset of the device, we see that the bootloader starts, but it is unable to read any valid image headers, so it's unable to boot anything. So the next thing that we need to do is to sign the primary image, which we configured before. So we go back to eSquare Studio and have a look at the signing key, which is here. Make sure it has the correct version number, which is 1, which is appropriate for the first version, and we can assign our initial project by calling sign. So now you see that a new debug file has been created, blinky image.bin, and this is the exact same file as blinky, but it's been signed. Now we have to load that into the target, and we'll do that once again with a script, and in this case it's the EKRA6M3 underscore app primary. Once again, bring in my command line file and execute, and it's loaded into the primary slot. So now we have a method to download updates of our firmware. Looking at the output windows of the Teraterm, we see that the bootloader has rebooted, and it's seen a valid application at offset 10,000, and it jumps to the first image slot, and that calls the menu that we have in the first application, which shows the display information, which enables a download of a new image and reboots the device. Now if we now press 1, we can see the original image, or the first image, revision 1, starting at 0 with this offset, and then within the second image slot is empty. Now we must configure an updated version of the application for the secondary slot. So once again we go back to eSquare Studio and have a look at the blinky thread. This is the line where the 3 LEDs are flashed, so we can reduce that by 1, and now only 2 LEDs are flashed. We can build that project, and to indicate that it's a newer version, we modify the revision number with the text editor and we give it a number 2. And now we must sign the image which we just created, and now it's been set to 1.0.2, and we go back to our terminal windows. Here we see the terminal windows, and here the menu of the MCU Boot. We can download a new image by pressing on 2. First, the secondary slot is checked and erased, and the start of the X modem transfer can be done by clicking on transfer, X modem, send, and browsing to the blinky image file we just created. It's downloaded to the secondary slot, and to view the contents of the secondary slot we press 1, and here we see that the primary slot is now revision 1 and the secondary slot is revision 2, but obviously this revision 1 is still being executed. To upload revision 2 to slot 1, we press 3 and the target is rebooted. Here you see on the terminal window of the bootloader that the primary slot is erased, the secondary slot is copied to the primary slot, and the bootloader is once again started at offset 10,000. And now we can view the target board, and we see that 2 LEDs are flashing. If we once again press 1 to display the image slot info, we now see that the revision 2 has been transferred to the primary slot and the secondary slot is empty. This concludes this demo. Implement the MCU Boot features in your next application. The presentation and example project are included in the downloads. And in closing, I would like to thank you for your attention. If you have any questions or recommendations for future videos, don't hesitate to contact me on this address. Thank you for your time.